Hey, this is Kenyon Conti, and this is my Lab 3 Properties of Capacitors and Combination of Capacitors. So the first thing that we did was we analyzed parallel plate capacitor properties by looking at voltage, plate charge, capacitance, and stored energy. The area that we used was constant, and the separation that we used was constant. With the information, I plotted a plate charge versus voltage graph, which clearly shows the linear relationship between voltage and plate charge, given by the equation Q equals CV, where C is the slope of the line and the capacitance. In part 2, we did a simulation of an electric field in a parallel plate capacitor, which I had to run through Java. And there were a lot of good takeaways from this, specifically that inside of a capacitor, the electric field is generated between the capacitors, and there's no electric field outside of the capacitors because the one positive probe is in one side of the battery and one negative probe is in the negative side of the battery. This was a graph that I used for electric field versus voltage, and the graph shows a linear relationship for the parallel plate capacitors given by the equation E equals VD, where V is the voltage and D is the distance. We can see as the distance is decreased, then the electric field is stronger. Something that was challenging in this lab was this part with the capacitor of the dielectric material. It was kind of hard to visualize this as we were using different types of probes such as Teflon, paper, and glass. So my graph looked a little funky right here, and these little bumps are due to the changes in the dielectric constant K, which we were using for different materials. The last thing that we did was simulation 4 and 5, where we had a big table here analyzing what happens when you connect and disconnect a battery probe. We can see the changes in total stored energy, changes in voltage, changes in capacitance, and changes in plate charge as the gap in the area are changed.